Try now?
Okay, can you hear me now? Okay, we're back. Can somebody say something out there?
Yes, we can hear you.
Good. Okay, I can hear you too.
Thank
Thanks, Jane.
you.
All right, perfect. Thank you. Okay, so first comment is we're going to transition and study periodic waves starting next week. Right now, we're finishing with some material on systems, stability of shock waves. And where we stopped was here. We wanted to study, we were talking about the dispersion curves around a constant solution. And so we want to study the real part of the spectrum of the Fourier symbol, which looks like this. And we want it less than or equal to negative theta k squared over 1 plus k squared. And this is called the dissipativity. And we saw that low frequency dissipativity was it's pretty clear what it is. High frequency, in principle, you could compute it, but it doesn't look nice. And so now we're going to show this very nice circle of ideas that dates back to the Japanese school in the 80s. And some names are Ukai, Matsumura. I'm skipping many, I'm sure. Nishida, Nishihara, Kawashima, and Shizuta. Especially, there's a nice book by Kawashima that explains all these things. Okay, so here's the idea. And I view it's a generalization of the Friedrich symmetric theory in a way, and lacks good enough observations about symmetrizability. So if there is a convex entropy, theta for, dt w plus dx, f of w equals, now we have a viscosity, and it must be viscosity compatible. So we want d squared theta b should be symmetric positive definite.
Sorry, what is in the argument?
B of w, sorry, just w. So it's quasi-linear, no worse than that. Not fully. Okay, so equivalently, or actually pretty much equivalently, we could take A and B, positive semi-definite. A and B symmetric, symmetrizable, but without loss of generality, both symmetric. And B positive semi-definite. So, and many physical systems have this property, including gas dynamics, isothermal landfall, and MHD. Okay, so then let's see what we get from this. Okay, now we'll look at lambda v equals negative I k a minus k squared b v, the eigenvalue equation. And if we take the real part of inner product of v against lambda v, that will be the real part of the inner product of v against negative I k a v minus k squared b v. This will be real part of lambda v squared on the left. On the right, we will have, since this is symmetric, 0 here for the first term. And for the second term, we'll have minus k squared v, v, v. And here we're using again symmetry to see that. So this one vanishes because IKA is skew. This one is real because k squared a is symmetric. Okay, and so we have that. Therefore, we have real part of lambda of k is less than or equal to negative k squared v, 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 which is less than or equal to 0. That's all we get out of that, because v is in general only semi-definite, for example, for isothermal gas dynamics, as we saw. But it's less than or equal to, okay, let's just say more. And it's less than 0 unless, well, unless v, v, v equals 0, or v is in the kernel of b. And let's see, is that enough? Yeah, but now we get more. Now go back to the original equation, the eigenvalue equation. If v is in the kernel of b, this term is gone. And that means that v must be an eigenvector of a. So, and v is an eigenvector of a. So two bad things have to happen. Otherwise, it's strictly negative. So now in comes genuine coupling condition. Which I just write GC. It says no eigenvector of A is in kernel of B. That's an assumption. This assumption rules out the bad possibility. Oh, there. Let's see. Or k equals 0. K equals 0 is if k equals 0, this is 0, no matter what. But anyway, we know that the eigenvalues pass through 0. Okay, so all right, so now, but here's the and this is going to be necessary for dissipativity. Okay, so dissipativity condition requires that the real part of the spectrum must be strictly negative when k is not 0, because look at the right-hand side. It will be only at 0 can it vanish. So this is needed. And let's just show that this is sharp, right? Because otherwise, I could take, for example, I could just take A to be, say, 1, 0, 0, minus 1. I could take B to be 0, 0, 0, 1. And you see that the spectra decouples. I'll get this, the symbol would be IK, or negative IK plus IK 0, 0, and then minus k squared. And so the spectra are negative IK and IK minus k squared. This one, which reflects the fact that the first coordinate obeys a hyperbolic equation. There's no damping and there's no coupling to the other term. So it's like there's a hidden scalar conservation law. Why do I have k squared here? Well, from the symbol. The symbol is yeah, this one, yeah. Yeah, so I'm putting it together in one. but it doesn't, yeah. And the reason is, right, because d1 dt v1 plus dx v1, yes, sorry, or minus dx v1 equals 0 in this system. So it has no damping and it has no coupling. So the genuine coupling is important here. Okay.
It will be a hypothesis to go.
Yeah, this will be the hypothesis. Yeah. And the theorem will be, now I'll state the theorem. Okay, so. Okay, so for A, B, simultaneously symmetrizable. Okay, without loss of generality symmetric. And B greater than or equal to 0 plus the genuine coupling condition, dissipativity holds. So for all, low frequency, mid frequency, high frequency, doesn't matter, just holds. So that's a fantastic result. Despite, and we have it despite the absence of parabolicity in some modes. And this is, so I'll remark, it's also called hyperbolic compensation sometimes. And it's related to hypoelasticity and hypocoercivity. So when we have an incomplete primary derivative term, in this case b dx squared, it can the dissipation effects that we're lacking can be compensated for by lower order terms if we have the proper coupling. Same idea. Okay, so the proof. Okay, first we showed that real part of the spectrum is strictly less than 0 unless k equals 0. That was the motivating computation. Okay, next. Now, in the previous lecture, I did leave out A strictly hyperbolic, which can be removed with further discussion, but I don't want to discuss it. So we want simple eigenvalues. We have that the lambda j of k for k small are analytic with expansion lambda j of k is equal to negative I aj k minus beta j k squared plus higher order terms. And where beta j is equal to lj a r j. So here aj is the eigenvalue of A, Lj and Rj are eigenvectors that are associated with we showed that last time. That was by bifurcation from simple eigenvalue. And we factored out a k, and that was the computation we did. But so now, okay, so now we have that, so we know that this, and I've lost my, here it is. And oh, by the way, LJ equals RJ. By symmetry. So, okay, so beta J equals 0, which is equivalent to LJB RJ equals 0. But this is RJ inner product with B RJ. That vanishes only if RJ is in the kernel of B. And this contradicts genuine coupling, because remember, R was an eigenvector of A. So it's not allowed to be in the kernel of B. So thus, beta J do not equal 0. They have a sign. Well, what could their sign be? It cannot be negative. If beta J were less than 0, then the real part of lambda J of K would be, well, it would be equal to real part of negative IAJ, that's 0, minus K squared beta J plus higher order terms. And this would be positive for small k by the Taylor expansion. But that we eliminated at the first jump. All the spectra is strictly negative real part unless we are at 0. So now we're just perturbing from 0, and we see, well, we go somewhere, but we're not allowed to go into the negative side. Therefore, beta J is positive. And this gives us the low frequency dissipativity condition. Real part, which is just real part of lambda J of K, is less than or equal to constant times K squared. That's all we need, but here's our constant, the smallest among all beta J's. So that's done. What about medium frequency? Well, this is just we just want real part of lambda J of K less than or equal to a small constant, because let's here you go. Yeah, here it is. When K is bounded away from 0, this just says basic or K is bigger than any small constant. Yeah. Then this is just boundedness by a small number. Okay, but this follows from the fact that real part of lambda J is strictly less than 0 plus continuity of lambda J plus compactness. Because we're on, this is the medium frequency is K less than or equal to a constant, bigger than or equal to 1 over that constant. So it's a bounded set.
Is it minus beta?
Oh, minus, I think minus. I want it to be strictly negative. Yeah. But I know that it's negative. I know it's continuous and it's acting on it's varying on a compact domain, so it's strictly negative. So that one's always free. Okay, so now that leaves high frequency. And this is also was the one where we kind of stopped before. That looks a little hard, right? It would be hard to do directly. But now we pause for a lemma. Okay, the lemma is, under the assumptions of the theorem, there exists K skew symmetric such that K, so the real part of K A plus B is definite. And when I say here, by real part of a matrix M, I mean M plus its transpose times 1/2, the symmetric part. So some people call this symmetric, you could, different notations. So just the symmetric part. So what I'm saying is that Ka plus Ka transpose over 2 plus B bigger than zero. That's what I want. Okay.
The real part of a matrix is a matrix,
Yeah, it's a matrix. I just, maybe it's better to say the symmetric part. Yes.
but when you write positive, the matrix is positive. The matrix.
Yes, the matrix is positive because this is, I've made it symmetric. So I'm just saying it's a positive in the sense of quadratic forms.
And A was already symmetric.
It was already symmetric, but now I'm multiply it by a skew matrix K. That's going to help. Okay, not clear why, but I don't have a matrix. Oh no, this is okay. This is a matrix, not this is not the yeah, capital K. It's not the frequency little k. It's not the Fourier frequency. It's a matrix that I'm asserting the existence of. Yeah. Okay. Right. So this is what I want. And this is then equivalent to, so because A is symmetric, this is Ka minus A K plus B positive. Let's see. Oh, maybe I'll go up. I'll just go up here. Okay, so it's that's what I'm trying to prove. Whoops. Okay, first step. I claim without loss of generality, A is diagonal. And that's because I can diagonalize by an orthogonal change of coordinates. And therefore, that doesn't change any of the properties of skew or symmetry. Okay, so now B is equal to beta 1 through beta n, and then other things. Down the diagonal, it's exactly these coefficients that we computed over here. These are the, it's Rj against B Rj, but the Rj's are just the standard basis elements. So it picks out the diagonals. Okay, but also we have that let's see. K A minus A K Ij is equal to K Ij times Aj minus AK. And we can just see that because, let's see, well, when you multiply by on either side of a diagonal matrix, you just pick out row versus column.
Aj minus AI.
Yeah. Do. Yeah. AI minus AJ. Yeah. Or the reverse, but it's not going to be important. It just says that this is non-zero. So in other words, I can specify this completely. I can choose for I does not equal J. Of course, if I equals J, this is zero. That's not good. Then I have no control. It's just vanishing. Well, that of course, that's down the diagonal. But I can choose all the others. So how will I choose it? I will choose them to cancel everything that I didn't write. So to cancel the off diagonal part of B, i.e., I'll take K ij to be negative B ij over AI minus AJ. And that will do it. Now, I have that Ka plus B real part is equal to beta 1 through beta n down the diagonals with no other entries. And this is positive. And I'm done. It is really nice, nice level. You know, it's nice when things work. Okay. Okay, so, but I'm not done. Now I need to do the main result, right? I need to show high frequency stability, high frequency dissipativity. But what I'm going to do is, it's a Kawashima type. We'll call it this type energy estimate. So I'm going to start again with the fact that lambda V is negative IKA minus K squared B V. But I'll now take a more sophisticated energy estimate. I will take that, therefore, let's so I'll take lambda V real part against K I times little k plus little k squared V against lambda V. I'll take the real part. That's equal to, okay, so now we're going to get real part of K ik plus k squared V against all these others. And that will be something strange, but I'm going to simplify this. It's going to be real part of negative k squared times Ka plus B R plus order of K. Because I'm interested in the dominant behavior, and the dominant behavior will be there are k squared order terms. Okay, and if I can show that this has a good sign, then I'm in good shape.
This is a little K or a big K inside the bound? The big K.
There's a
it
big
might
K,
be-
which I tried to indicate by a bar, and this is also a little K. Yeah, plus little K squared. So what is this? This is like an energy estimate where I take, it's a higher derivative energy estimate where this would be for an H1 energy estimate, and this would be like H1 half kind of, yeah, anyway, but you see it's going to help. Sorry?
You have the identity matrix multiplied to square.
Yes. I'm using that convention if I just write the, yeah. Yeah. And now you see, I need only consider things that, let's see, did I do this correctly? No, it's, I think it's K to the fourth, isn't it? Yeah.
Yeah, the R I lost. Second one.
Okay, to the second line, I'm just collecting all the fourth order terms. And let's see if I have done this properly. So K, let's see, am I doing this right? Yeah, K, let's see, no, I did it wrong. I think this is right. Got to be careful. Let's see. Sorry. So we're going to get a K to the fourth. I will get oh, good. I think I just want. I think my problem is I just want this. Sorry about that. There we go. And now the second order terms can involve B, V, V. It can involve, let's see, I do need another, I'm going to need another term. Oversimplified. Okay. So I'm going to get the K squared term that I want. That's from this part. And that's the only thing I get plus low order terms. But there is a bad term when I have K against B squared. So I have K, little K, K, B, K squared, BV. I have that one. I have the cross term. That's this one against this one. That's not so good, but I have a good one. I have this is a constant, not a matrix. So BIK squared, I'm going to have a good term coming from B plus K to the fourth times C, and I'll have V, V, V. That's what I'll have. And then that's it. All the others are lower order.
It's the same as before, but we added a little constant times case. Oh,
Yeah, we have a little, well, times K to the fourth. So we've got a bad term that I didn't account for. We've got the good term that I did write down, and we've got a good term that now I've added this in. I thought I could simplify it, but I can't. I thought I didn't need this for some reason, but I will need it. And so, but now you see, this one is definite. This is the one that we just showed is good. Okay, this one, okay, it's good on the complementary, on the range of B. It's only bad on the kernel. It's not bad, it's neutral, it's zero. And this one Well, if V is in the kernel, it's 0. This one is this so this is like the projection of V onto the kernel. It's the order of that, but times k cubed. And this is k to the fourth, and this is k squared. Together, Cauchy-Schwarz will control this. But I do need a big multiplier here in order to do that. So that's why I had the little c there, because you see, it's not just automatic. Let's see, actually, I guess perhaps it is because of the k cubed versus k to the fourth. Yeah, maybe I don't even need that. Yeah. But anyway, for sure I can control it if I put another constant. So I'll get this is less than or equal to negative theta k, k squared. Well, what's this? This is
By in the matrix C.
this. Yeah, I do have to choose k as in the lemma. I'm choosing k as in the little c is it's supposed to be c times identity. It's a constant. Just take it big, but I think I don't even need it to be big. But what is this? This is real part of lambda. Plus times order of k squared. That's the main term, plus lower order terms. So dividing, I get that real part of lambda is less than or equal to negative constant.
K large.
Yeah, the k is large, so that's all I see. Sure.
K big. Largest.
Yeah, I just take the largest contribution, which is this one here, and there's nothing here, so that's going to be yeah, k squared. Yeah, there we go. And okay, so that's what I wanted. So this gives me real part of lambda less than or equal to negative theta. And there's something else interesting. What if I had written what I really want is a resolvent estimate, you know, in this business, and the resolvent would work just fine. The same energy estimate works to get a resolvent estimate. And with modifications, if you have a shock wave with small variation, small amplitude, this same energy estimate will give you high frequency resolvent estimates. As we got them very easily with strict parabolicity, but this is not easy. This is very ingenious, I think. But anyway, it's known. By now it's known, and so you can use that. For large amplitude, you have to use some tricks. There are more tricks, but I'm not going to go into those. Not very hard, but
The part that ingenious is the presence of this matrix K.
Yeah.
Because the other terms are like.
yeah, this is the K was obtained in this lemma by using the. So yeah, right. So we took this matrix perturbation, which is very complicated, and replaced it by a structural condition. And K, people sometimes call K the Kawashima compensator. I like that term. It's compensating through hyperbolic effects, right? Because it's really interacting with A, with the that's the hyperbolic convection, in order to replace missing diffusion in the estimates. And let's see, what else should I say? Well, here, actually, we can control everything. We can, in the constant coefficient case, we can get the whole, we could do all three cases at once. If it were, once it's variable coefficient, you get a high frequency estimate only, because there are commutators that come in at the lowest order, and they're not of good sign. You don't know what they are. So it doesn't all close, but you still have the high frequency estimate. even with, that's why variable coefficients can still recover part. Okay, so any questions? Yeah, that's a really fantastic, yeah, fantastic progress. Okay, so let's see where we are. Going back to our starting point of shock stability, we have sigma essential. The essential spectrum of L is understood. Meaning when you have the structure of most of the physical systems, but not all, but most of them, you can just directly verify the dissipativity condition by the Kawashima conditions. And dissipativity was exactly what we needed. I'll draw it one more time. Here's a picture of the dissipativity condition. It says that all of the spectral curves are quadratically tangent at the origin, and then for large values, they have a spectral gap from the imaginary axis of theta. So they're strictly negative up high, and at the low frequencies, they're quadratic, at least looking diffusive. So that's enough to get started. One. Two, we had that the lambda j of k were negative aj k minus k squared beta k. And this was enough to get the to do the resolvent, low frequency resolvent bounds. That was the structure we used. It's the same as scalar conservation law. So we're and we have high frequency damping. So we need the point spectrum of L be contained in the set where real part of lambda is strictly less than 0, union 0. We can't avoid that. There's a translational eigenvalue, and then plus simplicity of lambda equals 0 as a root of the Evans function. Which was d of lambda was determinant of a certain matrix M of lambda that came from the transition, the matching condition. Okay. Filtered through some changes of coordinates that we don't know. So I'm going to now talk about these last two things. So the first one is the spectral stability. Point spectral stability, which is an eigenvalue problem. How do we treat that? Well, in the scalar case, with Sturm-Liouville theory, but that's very special. It's not going to help us for systems. But historically, there's an energy method. This goes back to basically Jonathan Goodman, who did the first result for systems. And it's the antiderivative method, it's sometimes called. And it's going to give stability for zero mass perturbation. So you start with, and I can do this for burgers to give you the idea, or any scalar conservation law, but let's just do burgers. So we have WT plus W squared over 2 sub x equals WXX. A stationary shock W of XT identically equal to W bar of X. We linearize and we get VT plus A bar VX equals VXX. And okay, so here's the idea is, so long as we look at, and this is, sorry, linearized, right. Okay, so long as we perturb this, as long as we take integral of V equals 0, that's what I mean by zero mass. Then we can take capital V, integral from of x defined as integral from minus infinity to x of little v of x dx, and work with that variable. And the reason we need zero mass is we need capital V to vanish at both infinities to still be in L2. So I'm going to change to the eigenvalue problem. So it's just V check lambda plus A bar V check X equals V check XX. Okay, and if we integrate it, we get lambda of capital V. I'll drop the checks. Plus A bar V sub X equals VXX. So we just changed the order of the derivative and the multiplier. That's all. But why I like to go, and here we'll take lambda does not equal 0. Lambda is not equal to 0 here.
The second equation from the bottom,
Uh-huh.
is it a little v or a big v?
This one is little v, small v. This is small v. It's the same structure, but now the structure changed. The x derivative moves inside, and this is the one I want. Yeah. So, okay. And by the way, I know by looking at the dispersion properties I just showed, or remembering that they're explicit for burgers, I know that any decaying solution at infinity actually decays exponentially. So long as I'm to the right of this spectral curve, which means basically anywhere for real part of lambda greater than or equal to 0, which is what I want to eliminate. If lambda is not 0, well, it's actually exponentially decaying. And so that makes it easier to see that then V of x would still be in L2, say. Otherwise, maybe I have to think about it a little bit, but I don't really have to think about anything. This is perfectly good. So if I have an eigenvalue for little v, I will have an eigenvalue for big V. Well, now I'll show that that can't happen by this energy estimate of Jonathan Goodman.
Yeah, we will not have spectral point spectrum.
I'll show there's none. Yes, right. This is the idea. Okay, so this is Goodman. 84, I think. It's okay. Short, not so long after Henry and Sadinger did the scalar case, and this is the first system case, and I'm showing you the scalar part. There's also a system part, but this is not going to be my main topic, so I'll just give you the idea. So the idea is you just take an energy estimate. So you take real part of V lambda V. This is now capital V. That's V against, okay, negative A bar V sub X plus V bar VXX. And this one is equal to, okay, the first one, so by parts, integrating both by parts in different ways. This one you have to do more than one integration by parts to see this, but it will be plus 1/2 dA bar over dx v. It changes sign and the derivative goes on to a, you get a 1/2. And the next one is, well, vx squared. Let's see. Yeah, that is correct. And the real part is important, otherwise this isn't true. Okay, but now let's remember a bar of x for burgers. A bar of x is df over dw of w bar, and f of w is w squared over 2. So this is just w bar. This is the wave itself, and w bar is, because it's a scalar, it's the solution of a scalar ODE, it's monotone. And remember that the left state must be bigger than the right state for burgers. This is monotone decreasing. So therefore, this is less than 0. It's good. They're both good signs. So we find that this is less than or equal to 0. And strictly less than 0. And by the way, and this is, of course, real part of lambda times v squared. So this is strictly less than 0 unless what? Unless vx, okay, vx squared equals 0, and v is identically equal to constant, but it's vanishing at infinity, so it must be identically 0. So it's trivial. This is not the case. Contradiction. So it's strictly less than 0, and that contradicts. That tells us that real part of lambda must be strictly less than 0. Fantastic. That's a beautiful proof. And okay, to do the system case, there were some other very clever things that Goodman did, and they're very important. For example, in the large amplitude damping estimate that I mentioned, it's crucial to use some of his tricks to deal with coupling terms. So this is not the only thing. Okay, so that's basically what you get. But what you don't get, that leaves, okay, so that leaves that leaves real part of lambda, that leaves lambda equals 0. And by the way, or also large amplitude. So I showed you for Berger's equation. Berger's equation is a good model of small amplitude shocks, but not necessarily large. So Goodman's result was for small amplitudes. And I should mention that almost the same time, Matsumura and Nishihara showed for gas dynamics. They showed the same result. So Goodman actually assumed strict parabolicity, though that's in the looking back not needed. This one used these Kawashima estimates and showed it for the physical equations. But both of these are for small amplitudes and 0 mass perturbations. And so when you go to the nonlinear theory, a lot of the difficulty, if you recall, was in the outgoing waves, the diffusion waves that carry mass. So this is the contribution of my advisor in 87, I believe. he gave the first ideas how to handle the diffusion waves, and it has metamorphosed over the years to what I presented. But okay, so what we've done kind of is we've connected, and we've gone from the zero mass. That's one thing we've done is our results show that if you have zero mass stability, then you have nonlinear stability with all the estimates that we gave. Okay, and that becomes important because there are more recent works by Matsumura and by Feimin Huang, who is now, I think, director of Chinese Academy. And they are for arbitrary amplitude shock waves of the isentropic gas.
Non-zero mass.
No, for zero mass, because it's an energy method. It's similar. It goes back to this kind of approach, but very tricky estimates.
What's the idea for the non-zero mass?
For non-zero mass, well, once you know that, so zero mass is good. Yes, I forgot to tell you an important fact. All right. This is the linking fact. I think I forgot the important fact. The important fact is, let's see, maybe, let's see, did I already show it? Let's see. Oh, I showed, oh, right. So suppose we have lambda V equals negative A bar V x minus B bar Vx x, non-zero mass. Integrate both sides. Integrate both sides. This is a perfect derivative. It integrates to zero. So I see that if lambda does not equal zero, then V is zero mass. Yeah. So earlier I showed if V is an eigenvalue and has zero mass, then capital V is an eigenvector, is an eigenfunction. But actually the zero mass was not necessary, except at lambda equals zero. Thanks for that question, because I left it disconnected. So if you show zero mass spectral stability, that implies non-zero mass spectral stability for every eigenvalue except zero. And actually that makes some sense, because at zero there's a difference between the integrated and the non-integrated. There's a translational eigenvector V equals dx W bar, but capital V would then be the integral of dx W bar, which would be W bar itself minus W minus. And that would be decaying at minus infinity, but not plus infinity. It would not be an eigenfunction. So there is a difference in the spectra. Okay, so, but however, these newer energy estimates that have been proven, I'm really surprised. They're fantastically clever estimates, and they work for all amplitudes, small to big, every shock that there exists. I don't know of one for full gas. Okay, but they have that. So now put these two things together, you have a full nonlinear stability result for isentropic gas with all reasonable equation of states and viscosities, really, I think it's fair to say. And so that's good, because in nature, shocks are pretty stable, at least 1D. Okay, so what?
Stability implies nonlinear stability.
Yes, at this point, but we have one more topic, which is lambda equals zero, and what's going on there. And it's actually very interesting. But let's take a break and we'll come back and start that. Okay. Yeah, I think Catherine will come back to join later. Yeah. Okay, so right. So here's okay, so now we're going to transition. We're going to talk about the Evans function. We need the Evans function to talk about the root at 0. Okay, so I'll just remind you, how did we define it? We took the eigenvalue equation, which is actually in second order, and we wrote it as a first order system in the augmented variable v dxv. And this is the main one, but actually we'll use this too. We use them both. And okay, we define the Evans function very simply in terms of these coordinates that we had changed. It's not clear what anything was anymore. So I'll give an intrinsic definition that's more useful for this purpose. So it will be capital V1 minus up to Vn minus Vn plus 1 plus up to V 2n plus determinant. So this is a 2n by 2n matrix. And here I've simplified the discussion by taking, I'm back to the strictly parabolic case. You can do similar things for degenerate matrices or general strictly parabolic, but the bookkeeping becomes, sorry?
What are the V's again?
The V's, this is in the, little v is in the eigenvalue equation. Big V is this, sorry, this is big V, and this is big A. Right, so this is big V over here. And this is what big A is.
No, that is.
Yeah, and
Parametric.
oh, these guys?
Yeah.
Oh, okay, so these are, I'm about to tell what they are. Yeah, okay. So here the V J minus are let's just call this E for eigenvalue, are solutions, are a basis of solutions decaying at x goes to minus infinity. And the Vj plus are a basis of solutions decaying as x goes to plus infinity. And by consistent splitting, there are exactly n of each. So how to see this? Take lambda, real of lambda goes to plus infinity and count. So if lambda goes to plus infinity, all the A terms are negligible, and you can see how many you have. Okay, and this would be for, okay, so this is on the domain of consistent splitting. I'm asserting consistent splitting, but and where does that hold? Everywhere except lambda equals 0, which is what the one I care about. But let's just clear that up. So okay, but near lambda equals 0. Okay, so I have to I can choose these asymptotic to some basis of the unstable subspace at W minus 0 and the stable subspace at W, oh, sorry, W plus of A. But near lambda equals 0, sigma U plus or minus and sigma S plus or minus extend analytically by a Taylor expansion. We did the eigenvalues. Sorry, mu j of lambda equals, what was it? Negative lambda over aj, lambda cubed over aj cubed plus higher order. It was basically inverting the dispersion relation. Mu is like ik. Okay, but we did this. We Taylor expanded around the origin. Well, we did for the scalar case. I guess, yeah, for the system case, I only did the dispersion curve, but I can invert that. I get the same thing. So we may have done actually this. Anyway, we have it. We can also do the eigenvectors in the same way. Everything continues analytically. And therefore, we can continue this subspace analytically, and therefore we can continue the Evans function analytically. But we have to be careful. So we only care, we want lambda, a real part of lambda greater than or equal to 0. So if lambda is not equal to 0, we're fine. Everything is completely determined at lambda equals 0. We have to find these subspaces by continuation. And what are they? Okay, so now we have to look at the letters, the second order version. Okay, now let's look at lambda v plus dx a bar v equals v dx squared v. If so there are different modes. I left out some modes. We also had mu j. It's equal to this, or it could be aj plus order of lambda. That was the other one. Those are the fast. These are the slow. So these are exponentially decaying at strict rate, even at lambda equals 0. What do these do at lambda equals 0? This is gone. So now, okay, the fast modes that decay, we can integrate this. Because we integrate these two things from minus infinity to x, and we get that AV from minus infinity to x equals dx v from minus infinity to x. By decay, we can remove the bottom. And therefore, we have dxv equals a bar v. First order description of the fast modes. And that will be important, and we'll remember that for later. What are the slow modes? Well, they are exactly going back to our asymptotic expansion. They are actually asymptotic to Rj0 with Aj outgoing. So on the left side, outgoing means negative sign. So this would be positive, but small. Positive on the negative x side means exponential decay, but slow. So that's a slow decay mode. On the right side, it's the reverse. But in fact, it's not just asymptotic to that. It's exact because if I take any, let's see, let me see what I want to say here. Is that what I want to say? No, that's all I'm going to say, I think. Yeah. Okay, that's good. All right. So that's all I need to know, turns out. Yeah, okay. And this is the 1D version was proved, I proved this with Robert Gardner in 98. And but that's R.A. Gardner. And then with Denis Serre in 1999 for multi-D. A multi-D version of this. Not multi-D. Yes, indeed, a multi-D. Okay, and somehow we proved this, but the full implications were not really clear until you write it in multi-D, and then it looks a lot better. And I will say also, it probably originates in Pago and Weinstein's work, 90s, on stability of scalar dispersive and higher order solitary waves. They have a similar I learned this kind of trick from them of how to deal with this. No, we don't do any shifting. That's all for the nonlinear analysis. This I'm just talking about the spectral analysis, and there was an estimate that they did that suggested this, what I'm about to do. Okay, and the basic idea is that, okay, here's the theorem. The theorem is for A strictly hyperbolic, A and B symmetrizable together, simultaneously symmetrizable, and okay, dissipativity condition. No, I don't need this. Just dissipativity. Dissipativity follows from those other conditions, but I don't need to assume it. We have d prime at zero is equal to delta times gamma, where delta is determinant of jump in W, R1 minus up to R P minus 1 minus R P plus 1 plus up to R n plus. And these are the outgoing eigenvectors associated with A plus and minus, plus df of W plus and minus. And it's a P shock, a lax P shock. So this is the Lopatinsky determinant of Miter. This is the inviscid determinant showing up in the viscous stability analysis.
The shortness, the jump of the.
Oh, this is the jump, yeah. W plus minus W minus. That's the one that we found in looking at the boundary value problem for the inviscid case. And gamma is a Melnikov determinant so with gamma equals 0 equivalent to transversality of the traveling wave connection. By which I mean, well, when we solve for the traveling wave, that's a heteroclinic connection between W minus and W plus in the traveling wave ODE system. Okay, and so typically it might look like something like this. It might be a repeller connecting to a saddle. Okay, that would be, relax, one shock. And transversality means that, okay, that there's this connection is this is a, okay, this is too simple because this is 2D. Every connection is transversal. But I want that this is the unstable manifold at one side intersecting the stable manifold at the other side. I want that intersection be transversal with a unique connection equal to the traveling wave. And
Formula to express this?
there is, and we'll just see what it is as we'll derive it, and we'll look at it and see, oh, that is a Melnikov integral, but it's a determinant. It's not written in a very nice form by which you would analyze it. Like when you do dynamical systems, you write it in terms of variational equations, and it's very useful. But this is not very useful the way I'm writing it, but it's more insightful. It will give you some understanding. Yeah, so maybe I'll just say something now. Okay, so simplicity of lambda equals 0 as a root of d of lambda equals 0 is therefore equivalent to delta does not equal 0 and gamma does not equal 0. And this is the inviscid stability. And this is the, okay, so this is something else. This is the Melnikov, this is transversality of the connection. So this can fail in two ways. It can fail by, so if we imagine starting at W minus, and we do this thought experiment along the shock curve, and we take W plus to be W of theta, as we did in the Vasseur condition. We just move along the curve, and we ask when, and we know, okay, we know initially, by the way, this is always going to be non-vanishing, and that's because we know that, why? Well, okay, we know this one. This one follows from an argument of Maida and Pagel, a small amplitude analysis of the connection problem. It's known. For many systems, you can see it clearly. It follows from Gilbart analysis, for example, for gas dynamics, not only at 0, but everywhere. This is always holding. In fact, for isentropic gas, which is a 2x2 system, transversality is automatic as long as you have a connection, because one side is full, is the whole space, right? You can only have a saddle on one side. It's always going to be either repeller saddle or saddle attractor, and it cannot fail to be transversal. So and in full gas dynamics, well, it turns out still true. Okay, so therefore, it's this one that's yeah. Okay, what happens if this one changes? Well, then we have this shock splitting. We'll talk about what that means in a minute. But let's see. Actually, maybe I want to talk about that right now. I think I do. Yeah. I want to draw a picture of this. This is really a nice. I like this picture, and I didn't do it so well before. Okay, so let's see. Is it time for that? Yes. Yeah. Okay. Yeah, I have to say Okay, now I have to say a bit more, so I'll come back to that. Let's prove the lemma first. Uh, okay, all right. Okay, so I have d prime of lambda, the determinant. Okay, I'm going to just use
Zero.
d prime of 0. Thanks. Multilinearity. By multilinearity, this is of the determinant. See, I hope I have it there. Let's see. Here it is. It's a determinant. That's all I need. So it's equal to d v1 over d lambda, v2 through vn, plus v1, d over d lambda, v2, v3 up to v, well, it's not up to 2n. Plus, etc. All possible, the derivative has to fall on only one, it's product rule. Okay. And I should have started with without loss of generality, take v1 equals dx w bar equals v2n. That's because I know among the decaying modes, there at minus infinity and the decaying modes at plus infinity, there is a common element, which is the derivative of the traveling wave. To make the calculations easier, I mean, it's some linear combination of these things to begin with. I'm going to insist that this one, I choose coordinates in which this one is exactly v1 and v2n. And the reason, yeah, okay. And the reason I want to do that is, and how does it simplify life? It simplifies life because if a derivative falls on v1, okay. If it falls on v2n, okay. If it doesn't, I always have v1 and v2n linearly dependent. So all the values in between are gone. So that's great. And this is why almost always you could take one derivative of the Evans function and get something out of it, get some kind of
Is it possible to choose both equals to that particular solution?
yes, because what I know is that so I have some freedom of choice in these bases. These are just basis elements for all the decaying ones.
The same V.
The script v, which is actually little v and dx of little v. So it's the expanded system. And I'm sorry. So in fact, let's see. Yeah. So okay. So I said this wrong. I really want little v1. Yeah. Thank you. Because if I take big Vn, it would be dx w bar, and then its second derivative. Yeah, you're right. That's confusing. Yeah, this is what I want.
Because we have a choice like this.
Yeah, but then this does imply that v1 minus equals big script v 2n plus, because they're just completed by their further derivative. So if the first element is identically equal, the second will be 2. So that's what I need for this computation. And then I want to do one more thing. I want to use the symmetry of the determinant to switch the order. This guy I want to move over here. I'll exchange. V1 I'll put over here. So I get determinant then of, but that changes the sign. So I'll get d over d lambda, d1 minus d over d lambda. That's a d lambda, b2n, b2 out to v 2n plus d w bar over dx and dx squared w bar. So the last one will be, or just say v1. I'll just say v1. That's nicer. Okay, so now I'm going to do a sort of a block determinant reduction. But to do that, I want to go back to F. Okay, this is for fast modes. And I saw that I could integrate the equation, and I get this. If I do the same thing for slow modes, and let's write it like this. dxv minus av will then be what? Now there will be a contribution from infinity. It will be rj plus or minus. It will be the value at minus infinity. But now if we look at this is a row operation. This is take the first row or the second row and subtract off a times the first row. So I'll perform this row operation.
Second line, the second box up there in the, what's the difference between the first box and the second?
They were for two different kinds of modes. When I had fast decay, so that means modes that actually decay at infinity for lambda equals 0. Then I get 0 on the right-hand side. It just came from the boundary contribution. And the slow modes, though, I know those are asymptotic to their first derivatives decay, but the function itself does not decay. So there's no boundary condition on this side, but there is a boundary condition on this side. And actually, it's not just rj, it's a times rj, which is aj, because it is an eigenvector. But that's really not so important. And so now I do the block reduction, and I get, okay, so I'll get d over d lambda v1 minus v2n. I still don't have that really worked out, but all the rest I have. So let's see. So what happens? So I get 0 everywhere I have a fast mode. And I will have 2n of those. They're in different spots, but there are, so k and n minus k, not 2n, there are n of them. And these, I just don't care what's on top. I'm sorry. I certainly do care, but it's just v n minus k through v n and minus and v 2n minus k. However many there are, let's see, up to v2n. Okay, whatever they are. All right, so, but this is 0. So what I'm going to get, and the other ones have not 0, but they actually have something up here, which I don't care, and then they have aj, rj. And I've got n minus 1 of those. So just by block determinant reduction, I get determinant of the guys on top. And these are all fast. Equals decaying through V, whatever they were, 2n minus something. 2V, 2n plus times determinant of, okay, what goes on the bottom row here. Yeah, whatever goes down there, we're going to figure that out. Right. And what goes on the bottom after this row reduction? So we've got R, R2 through Rn down here. And we've got something that goes in there. Okay, so now you see this is gamma, this is delta. We haven't shown that this is delta yet.
Can you do gamma?
So gamma comes from all these things because there are n zeros in the bottom. So therefore, this determinant splits into the product of the determinant of these elements on top. So these are all the fast modes from the left and from the right. That's what it is. And this is n minus k up to n with, okay, but I don't even know what the bookkeeping is, but all I know is there are n of them, and they're all the decaying modes.
And we have the
Actually, not all, because on the left, I've thrown away the derivative of the traveling wave. I've only counted that once. Otherwise, there would be n plus 1.
say n minus k, you mean you start at
I start whenever the fast modes, maybe I start with the slow modes and then the fast modes. I have to order them somehow.
so they are the minus one.
Yeah, these are the minus ones, but there are plus ones as well. There are ones on both sides. There are fast modes, and there will be at least one on each side because the derivative of the traveling wave. But I know that I have n of them. There are only n minus 1 slow modes because there are only n minus 1 outgoing directions, and all the rest must be fast modes. Those correspond to incoming directions precisely, and there are n plus 1 of them. But in this operation, I traded one of the, a derivative fell on one of the derivatives of the traveling wave, and it's not that anymore. The derivative of the traveling wave is only counted once. It only appears once in this formulation, and therefore, okay, so what is this? I said I'm calling it gamma, and now I claim it's a Melnikov determinant. Because think of the traveling wave ODE. This is the traveling wave ODE. It's exactly that. And I'm looking at all the ones all the solutions that decay at minus infinity, all the ones that decay at plus infinity. And on the left side, I'm throwing out the one that decays, the derivative of the traveling wave itself, and I'm asking that this determinant not vanish. Well, that's exactly transversality. Because failure of transversality means there's some direction in the linearization that I can move, and I'll be still satisfying the linearized equation. Other than I know that I can translate it, but that corresponds to motion along the traveling wave, which would mean I have to have the same element at minus infinity and plus infinity. But at minus infinity, I've removed it. I'm taking every other possible perturbation other than that. So I'm looking for a full rank up to translation. And that's exactly what this determinant tells us. It's not in a useful form at all. It's just abstractly, that is corresponds to transversality. And now I have to show that the other one thing is what I say. Okay, but that's a fun one.
The R1, Rn, Rn is the one that were already written there.
Yeah, so we're really close. We just need this. What we need one more thing.
Don't.
Jump is the first determinant.
Yeah, and that means what I need to show is this. The element that's left is well, I'm taking dx minus sorry, I'm taking a v dx v minus a v. Okay, but now instead of little v, I want dv over d lambda. Minus a dv over d lambda. And I want this to be, and I want that the jump in this, so between the v1 minus a v, well, let me write it out. I want that this is v1 and then minus the same thing. And this is so this is dv, sorry, 1, and this is dv2n, d over d lambda v2n minus a d over d lambda v2n. This is dx, yeah, that's.
It's V1 minus.
Yeah, this is v1 minus, that's important, and this is v2n plus. And this should be equal to, we hope it's equal to jump in w. That's what we want. And if it is, we're done. Okay, but now I go back to the, now I don't have this is not a big V, this is a little v, which is good for me. Because I know that, okay, I have lambda times little v plus a bar dx little v equals dx squared little v. So now whatever, if I take, now let me take a variation. And remember that I have analyticity and everything. I've defined these representatives v as functions of lambda analytically through the conjugation lemma. I know that there exist analytic representations, and this is what I'm working with. So this is just lambda dv over d lambda plus dx a dv over d lambda minus dx squared dv over d lambda. And there's only one term that I left out that I have to put over on the other side, which is negative v at lambda.
A bar is always bar, A bar, or it's something.
This is a bar, yeah, a bar here.
And in the white.
Oh no, this is a bar, yeah.
White line is A bar. Wait.
This should be a bar, yes. A bar. It should have a bar everywhere. It's varying, yeah, of w bar of x. So it's variable coefficient for sure. Okay, so at lambda equals 0, this term is gone. And this term, I know what it is. It's dx w bar. Well, lambda equals 0 and I equals 1 or j equals 1 or 2n for the two things I'm concerned with. I know that they're both initialized as derivative of the traveling wave. So that's what goes on the right. And on the left, I have just dx of a bar, let's just write v lambda, minus dx squared v lambda. And now I'll integrate from minus infinity up to x, as I did with the fast modes. And this is a fast mode, by the way. This is still fast, still decaying, even though I take a lambda derivative because I've chosen it as representative of a fast mode. So I get AV lambda minus dx v lambda equals. Now I get the integral from minus infinity to x of dx w, or respectively, if I'm on the right-hand side, I actually have to integrate from x to plus infinity to do this business, because that's where I know it decays. I only know it decays on one side, on its own side. And this will give me, but this is w bar minus w plus or minus, or let's say w minus, or respectively w bar minus w plus. And that means when I subtract these two and correct for having, I think I wrote this in the wrong order that I don't want. I want actually dx v minus av. That's the row operation I did, but I will get this because the w bar part, it's in common to both, that it cancels. Fantastic little things. Oh, respectively means I have the v1 that's at minus infinity. So I must integrate that one from minus infinity in order to use decay to cancel. Well, I guess since I know this one happens to decay, no, v sub lambda decays only at minus infinity. At lambda equals 0, it happens to decay at plus infinity, but at other lambda, v1 of lambda does not. Mhm.
It's a big V or is it small? Everything is small V,
This is all small v. Yeah, these are all small v.
but we have V minus V equals minus dx W bar. Yeah.
Yeah, because this was, sorry, this is v evaluated, okay, v of lambda. This is, I'm just emphasizing at lambda, whatever lambda is. That's silly. I shouldn't have written that. Let's just take that away. That was confusing. It's just period. But I remember that at lambda equals 0, now I use this. So I take the variation at lambda equals 0. Yeah, that's what I want to use.
Where did we learn that before? I mean,
We prescribed that. That was what all these computations were based on that. Yeah, so it wouldn't be, nothing we wrote would be true, except in that it would be something complicated that we wouldn't see much. But in this coordinatization, with this choice of basis, which is only specifying one thing really, then we can compute the whole way. And we find that indeed this difference is jumping W. We put it in, we've got it. So yeah, it's yeah. This is really a nice argument, and it's really just well, it's doing what Pagel and Weinstein did, but it was scalar, and somehow, I don't know, it just didn't occur to us at first to do this, but or second, but
it was kind of
yeah, that was a dispersive problem. Yeah, but after so you're going to write it as in augmented variables, so it will be v dx v and dx squared v, and now you have a matrix, even though it was a scalar problem, and it has a lot of similarity, and you'll cancel, I guess, just one row. I leave one row and cancel the rest, and yeah, they in some ways it's more complicated, but in some ways less. It's scalar. You have the higher order. Anyway, they came out with something that was very useful for them, and this is very useful for us. And so next time I'm going to tell, before we'll have one lecture of this and then start into the periodic, and I'm going to tell what you get out of this. You get quite a lot. You get the answer to the question that Ralph Menikoff or Bert Wendorf posed to me. What happens with this shock splitting business? And you can answer that. So that's a good stopping point. Okay, well, it's 5, so that's a good stopping point for today also. But Oh, yeah, this is, yeah, there are many more applications of the Evans function, right? So this is just, I just evaluated at its derivative at zero, and that gave a lot of information. But you can also use it to study the spectral stability problem as a whole, yeah, rather than energy estimates. No, I'm talking still about shock waves now. Yeah, yeah, in both, actually, in both.
It was indeed the spectral stability for they introduced the Evans function to study.
Yes, that's interesting. Okay, there it's a Hamiltonian problem. So they had some information to begin with based on like this Grillakis-Chatat-Strauss setup. So they know there is exactly one negative eigenvalue or zero.
It's simple.
And it would be simple, yeah. And so actually this computation, basically it's going to give you more than this. The reason is that we can actually continue the Evans function globally analytically. I didn't show that yet, but you can. Maybe I won't show that, but you can if you're careful. And then that tells you that as you're doing some kind of homotopy through different waves, well, at infinity, the Evans function never vanishes. And the Evans function is real valued on the real axis. So actually the sign of the derivative at zero, so here's lambda, real, and here's d. So we find some sign of the derivative. And we know some sign at infinity. So they had better agree. It gives you a stability index, a mod 2 stability index, which is the product of the two signs. And if it's positive, that's good, consistent with stability. If it's negative, that gives instability results. And actually, Gardner and I used this to get instability results initially, and we didn't really, yeah, spectral instability. But if you know there's at most one eigenvalue, mod 2 is very good. It's actually necessary and sufficient. So that is what they were able to do. And in some cases where, if I recall, I mean, also if Grillakis-Chatat-Strauss is necessary and sufficient, if you have a condition that so you have a skew symmetrizer in the evolution problem. If it's full rank, if it's surjective, then it's necessary and sufficient. But for higher order dispersive equation, it's not. It's a derivative usually, and it's not onto. So Pago and Weinstein were able to deal with that case using the Evans function instead. That's just one of the things they did. They did many things in those papers, but that was, I think, I recall, that's kind of a major point. So you still know it's, yeah, you still know it's at most one, but you don't know the sign anymore, for sure. I think I got that right, but anyway, yeah, so they had to use both. So we don't have that, so we can only say, we can definitively give you instability results from this index. But for stability, well, okay, we will know that we've taken care of the zero eigenvalue, but it is quite possible that eigenvalues can cross not only through the origin, but they could cross elsewhere. And okay, so I'll mention some comments about that next time. But it's a good starting point. And numerically, you can study if you have an analytic function. That's like a characteristic determinant for a matrix, right? You could use Rouché's theorem. You can look at Nyquist diagrams. You can do all those things. It's harder, but because you have to solve an ODE to evaluate it, but you can still do it, and it's been very useful. We've used that to analyze a lot of problems. That was my starting out. I thought this would be the way you do it, because how could you ever do a large arbitrary amplitude shock wave and prove spectral stability? But Feynman Huang and Matsumura and company, they did it. So, I thought maybe there's some really special system where you could do it, but probably not much. But people are ingenious. So who knows? But there will surely be some, you can always make up one that's not gonna be nice, and it might be, physics might give you one. So this gives us all it opens up different ways. We could always do it numerically. I actually thought in 1998, I had a student working on numerical proof. I thought there would soon be a black box that you just press the button and find spectral stability with guaranteed rigor. And that didn't happen, but I think it's probably likely to happen really soon with the speed of progress in that area. So, you know, anyway, lots of interesting progress. But at the same time, people are proving amazing results by hand. So who knows? Who will win? I'm hoping for the humans, but I'm betting on the the bots. Yeah. So, all right. I think that's it. Any comments from online or questions? Nope. Okay. All right. See you next time.
The talk, the first of talk is 1:30 to 30.
That's right, isn't it? Next Thursday?
That is the stock of the wind Peterson that probably everybody's interested. In a room, it's somewhere on the campus.
Do you think people at the uni will attend? Do you think that people will attend the talk?
Yes, there will be a lot of people because of the computer science. They took a big room. And then we come back here and we have.
Yeah, right. So we come back at next Thursday at
the
4.
next Thursday, Just, the talk will be just here.
Oh, great. Oh, okay.
The first day it's because it's more general.
But the first day is Wednesday, correct?
Yeah.
Right.
Yeah. Oh, so that doesn't interfere. Right. Yeah. So Thursday will work fine, I guess. We just,
We come directly from the health department, so 5 minutes or so.
yeah. So 4:05 or whatever, 4:10, and then we'll go. Sorry about that, but I think the talk sounds really interesting. Reading Alan Turing. That's wow.
I'm gonna fix the schedule. There you go.
Thursday.
Yeah.
is at the department.
So we'll have, but first we'll go with Federico, I guess. Which you Federico or other Federico on Thursday?
What, did again?
The 1:30 till 2:30. Okay. Good. That's gonna be fun. And then we get Avi Wignesson. Should also be pretty good.
The